after chapter 3, 4, and 5, this part of the chemistry is not going to be as calculation intensive, but there's a lot of memorization involved in here. And we ask you, for example, to determine which of the diatomic molecule is more polar between the two groups or within each group there. So boron to fluorine, boron to chlorine. Okay, so we need to take a look at the value for the electron activity there. And then silicon and oxygen and the phosphorus, phosphorus. Which one is more? Well, this one is easy to say. Well, phosphorus, phosphorus, that's pure covalent. Okay, silicon, oxygen, they're different. So obviously, this difference is going to be greater than this difference. And between these two molecules, their silicon oxygen bound is going to be more polar. And what about the boron, fluorine, boron, chlorine? Well, we can look at the values there. The difference in terms of the electron activity. Okay, so 2.0 boron chloride, okay, and 1.2 boron chlorine. So from here, we can draw a conclusion. And this is a much more polar bound. Well, this is 2.0 or greater. This could be classified as an ionic bound. Okay, so ionic bound versus 1.2, a polar bound, and we can say the polarity in terms of polarity here. Well, boron chlorine bound is more polar than boron chlorine. This silicon oxygen bound is more polar than phosphorus phosphorus. So we will give you the table of electron activity for each of the elements if we ask you to determine the polarity. Okay. Now the thing here is that many atoms, many molecules are not just composed of two atoms there, and we have polyatomic molecules. How do we determine the polarity for a polyatomic molecule? Well, this is a more complex problem there because the factors affecting the polarity of a molecule, not just the chemical bound in there. When you have just one bond between two atoms there, you simply take the difference in terms of electron activity, and you determine whether a molecule bound is polar or non-polar. If the bound is polar, the molecule is polar. But for polyatomic molecules, there we have to take into consideration not only about the bound polarity. Do we have lone pair of electrons? The electrons not being used to form chemical bound, and whether or not we have a polar bound in there, and also what is the geometry of the molecule. So this is the topic that we will come back in chapter 10 after we take a closer look about the electron distribution within polyatomic molecules. Okay. So we'll take a look at this particular topic again in chapter 10. Our next learning objective in chapter 9 here, we're going to look at the structure of the covalent bounded molecule. We want you to be able to understand how are the electrons being shared among different atoms in the molecular compound there. So this is the topic where we introduce Lewis structure. Now those people who are planning on taking more chemistry classes there, Lewis structure, and this is something that you will hear on a regular basis, especially if you're going to take organic chemistry. Lewis structure is very important. So we need you to be able to draw Lewis structure for covalent bounded molecules. We need you to be able to define and give examples of what we call resonance, a very important concept in organic chemistry. So now you know why we have Chem 101 as the prereq for Chem 201 organic chemistry. We are introducing a lot of basic concepts in general chem there, and then when you get into organic chemistry, we're going to use these theory to understand how organic molecules behave and react with one another. Okay? So we also need you to be able to draw Lewis structure for molecules with exceptions to what we call the octet group. We will introduce what is octet group. So we will try to follow the octet group when we try to learn how to draw Lewis structure, and then for every rule, for every regulation, there's always exceptions there. We want you to understand what are those exceptions, and under what kind of situation you have an exception. Okay, so Lewis structure, when you talk about the Lewis structure, obviously Lewis is the name of the person, Gilbert Newton Lewis, another American chemical chemist, and he made tremendous contribution to modern chemistry. And look at his life, 1875 to 1946. In his 70-some years of life, he has been nominated for the Nobel Prize for chemistry more than 30 times. Never got one. That's kind of impressive. Well, the speculation goes that he died in 1946, and because one of his students, after graduating under his advising, and after graduation, his student went on and worked in the area of chemistry, and his student was awarded a Nobel Prize. And then the school was actually recognizing the student's achievement. So bring him back and give him an honorary degree. So he met with his old advisor. They went out for lunch, and after lunch, they came back. And the speculation says, well, well, at least that's what the witness said. Louis appears to be very stressed. So he went back to his lab and worked on his project there. And 2 hours later, he was found dead from cyanide poisoning. So that's a very sad story. That could be, student being awarded a Nobel Prize and then coming back and being recognized by his school, and then that may be the last straw that break the back of the camel there. But it was a sad story. But nevertheless, the contribution that he made to modern chemistry help us to understand the behavior of organic molecules. And he pioneered this approach by, this is how we're going to determine how electrons are being shared by non-metal elements there. And based on that theory, we understand how the electrons are being shared for organic molecules there. In addition to more than that, and just in pretty much every covalent bonded molecule, we will be able to draw their Lewis structure. Okay, so, and the element of, what he proposed here is that when you draw a Lewis structure, basically we're trying to understand, once we know, based on the quantum theory, once we know how the electrons are being shared, they're being distributed around a particular atom there, then when atoms come together, they're going to share their electrons when they form molecules there. So when you draw a Lewis structure for an individual atom there, and the proposal that he gave here is that when you write the symbol of the element down, that chemical symbol, see carbon, C for carbon, H for hydrogen, okay, that symbol of the element represents the core electron and everything else in the atom, except the valence electron. So it's the nucleus, it's the core electron. So when you put carbon down, that letter C represents 2 of the 6 core electrons. It also represents this total of 6 protons in here. Okay, you have carbon is group 4A, so we have 4 valence electrons. And he said, to represent the distribution of the valence electron, we use a single dot to represent a particular electron. So for carbon, we have 4 valence electrons, group 4A. We put a dot on each side of that atom. So each dot represents 1 valence electron. So this